Okay, it's 1, so I'd like to get started. Today we're going to be talking about some concepts in machine learning rather than particular models or classifiers. Many of the lectures in this course, like last class, we introduced decision trees. We'll introduce often one method per class, but today we're going to be talking about some fundamental concepts. Okay, so last time we talked about decision trees and we introduced this notation that we'll be using throughout the course for supervised learning, which again means you have input-output pairs and you want to learn to predict the output given the input. And so we talked about this notation. We had n being the number of objects, d being the number of rows, and once again, there's a document about the course notation on the website. So x, y, and d. And the most trippy thing about this is that sometimes something is a vector and sometimes something is a number, and you have to infer from the context. So for example, xi is a vector, but yi is a number, or a scalar, single thing. Okay, so we talked about supervised learning with the food allergy example, but the whole paradigm that we talked about last time can be applied to so many situations where you have these input-output pairs. So for example, spam filtering. When you mark something as spam, that is now a yi for the spam filter because it knows something has been marked as spam. If you reply to it, it's probably not spam, so maybe that's another label. Character recognition, faces, cameras, Facebook, speech recognition, all that kind of stuff. So it's a very common situation that you have these input-output pairs. For speech recognition, it would mean you have a corpus of audio clips with the correct transcription, and you want to learn from that to do speech recognition on new samples. Okay. So today we're going to talk about overfitting and underfitting and what we call in this class the fundamental trade-off of machine learning that some of you alluded to last class. So I'm going to switch into some code in Jupyter and then I will switch back to the PowerPoint. And as usual, this is posted. You can look at it in the browser. It'll be static. You can download it and run it. If you don't know how to do that, check Piazza. People have been asking about that on there. Okay, so I'm going to import some stuff. And I'm going to load this handwritten digit data set that's very famous in machine learning. This is actually a smaller version of the most famous one. So the inputs are images of digits. So they're pixel values, like we talked about on the very first day, or second day, I guess, how you just look at all the pixel values, and the outputs are the actual digits. So here's an example of an xi. This is one 8 by 8 pixel image. This is a 0 in this case. I can rerun it. It's just picking a different random example. So it's actually a bit hard to see when you're very zoomed in, but the farther away you are, the more it looks like the right number, and that's just because it's such a low resolution image. So my n is about 1800. I have 1800 of these images, each with a corresponding label. The label is an integer from 0 to 9 saying what the digit actually is, and my supervised learning task is given a new image, can I automatically predict what digit it is, and then I could use this for, say, the post office uses it to automatically scan postal codes and sort mail or checks, etc., etc. Yeah, what's your name?
Fed.
Fed.
Is there a problem to me that looks ambiguous, F? Like, it could be a 9 or an 8. Is it bad to give these kinds of training examples to the computer? Because I can't even tell.
Interesting question. Okay, so the question is, this looks ambiguous. Is it bad to give these kinds of training examples? So I guess in a way, this is probably better than nothing. If you wanted, there are ways to maybe communicate that ambiguity to the algorithm, which we'll talk about later. You could even have the exact same image in there twice, in one case labeled as an 8 and one case labeled as a 9. And you would hope that wouldn't break whatever we were doing. In some cases it might, but usually all the methods we've been using will assume some amount of noise and we'll be able to deal with it. Okay, so we talked about exploratory data analysis last week, so I thought I would just start with some of that. It's more fun if you don't get to see it in advance. So I can make a histogram of the y values, and this just shows that we have about a uniform distribution of the digits 0 through 9, so about the same number of examples of 1s, 2s, etc. And in terms of the histogram of x, I can see that there's this big peak at 0. Does anyone want to try to interpret that? Fed.
Most of the surrounding stuff is black.
Right. So in this case, 0 encodes a dark pixel, and that's most of the pixels. So the digit itself is a brighter intensity, and then we just have a bunch of dark pixels that are 0 or close to 0. Probably exactly 0 in this case. This is a very toy version of the data set where the x doesn't even take on that many possible values. Okay, so we talked about decision stumps last time, but we didn't actually run them on anything, so let's run them. So I have imported the decision tree classifier from scikit-learn, and I can fit. So max depth 1 is the same thing as saying I want a decision stump. A decision stump is a depth 1 decision tree. And then I can fit it on my data set. I get some output that I don't really want. And I can actually visualize it using this nice package GraphViz. And it doesn't quite fit on the screen, but what you can see is that the split that was chosen was the feature number 36 being less than 0.5. The x values happen to be integers here, so it's basically saying all the zeros go to the left, all the non-zeros go to the right for pixel number 36, whatever that is. So the first split says if pixel number 36 is 0, I'm going to say this is a digit of a 0, otherwise I'm going to say it's a 1. So that's what this class equals 0, class equals 1. So not a very sophisticated model so far. But we can also see on each side what kind of a histogram of the values. So there's a whole bunch of 0 digits that got moved to the left, and that's why we're predicting 0. Any questions or comments at this point? Yeah, what's your name?
Vanessa,
Vanessa?
are we ruling out the other numbers? Now we're just saying it's either a 0 or a 1?
Yeah, so there are 10 possibilities, and we've only used the decision stump, which is not a very good, not a very sophisticated model. So in this case, it's never going to predict anything else, which is really, it's obviously not going to do a good job. Yeah. So here's another thing I can do. I can check the error rate, which is something we talked about last time. How well is this thing doing? And so here's how I'm going to do that. I'm going to call stump.predict on x. Notice that with fit, I passed in x and y, and with predict, I'm not passing in y, because I'm just making predictions. The whole point of the predict function is to produce y given x. That's the whole point of supervised learning. So I'm just passing in x, and I'm getting out this y hat, which is a vector of length n, where for each row of x, I'm producing my predicted class, which will itself be an integer 0 through 9. And if you don't believe me, I can look at it. Oh, lost my toolbar. Okay. Right. So, oh, I said 0 through 9, but because of what Vanessa mentioned earlier, it's only predicting zeros or ones because it's this really unsophisticated model. So that's why the output looks like this. And the next thing I can do is compute the error rate. So here's what I'm doing. I'm saying y not equal to y hat. So y and y hat are both vectors of length n. I'm doing a comparison between them, which does element-wise comparison. So for each pair of elements, it runs the not equals, returns either true or false, and then y not equal to y hat evaluates to another array of length n of type Boolean that tells you in each case, was that true or false? So I could also show that to you. So this evaluates to a Boolean array of length n, telling me when they're not equal. And then I'm just summing them up. So I'm summing something of type Boolean. NumPy automatically typecasts the Boolean to an integer. So true becomes 1, false becomes 0. And therefore, the sum tells me how many trues, which tells me how many mistakes I made. And then I divide by n to get it from a number of errors to an error rate or fraction of errors. 80%, which is pretty much because I'm only predicting 0 or 1. So, and we already saw that they were uniformly distributed, so I'm probably getting most of the zeros right, most of the ones right, if not all, and then practically everything else wrong. Any questions or comments about this? Name?
Oliver.
Oliver.
So for the second branch on that stump there, we chose class 1 sort of arbitrarily because class 3 also has like is also there.
Correct. So in the second branch here, we chose class 1, even though class 1 and class 3 both have 182 examples. That was just an arbitrary choice. I don't know exactly how scikit-learn does it. Maybe it's random. I guess we could try it again. I don't know. It's probably not random because after 5 times. So maybe it just takes the lowest one. I don't know. OK. Good. So we've done better than random, but still not that great. Yeah, what's your name?
Arthur.
Arthur?
Yes. You are predicting the same.
Oh, much louder, much louder.
You are predicting the same model that you trained it like.
Correct. I am predicting on the same data that I trained on,
Yes.
which is why I'm very soon going to call this the training error instead of the error rate. Yeah. Correct. So this just tells me how well did I do on my training data. It doesn't yet tell me how well do I generalize, which is the whole purpose of today's lecture. Yeah, name?
Edwin.
Anthony?
Edwin.
Edwin.
The array in the value variable, are those the index of the labels in the original data?
Which array?
In the tree, there's an array called values.
Yeah, right. So in the tree, this is saying that I started with 178 zeros, 182 ones, and then after I split on the left, I was left with 174 zeros, 0 ones, etc. So it's basically a histogram. Okay. Okay, so let's do depth 2. So same data set. This one is definitely not going to fit. I guess I could temporarily zoom out. I'll zoom back in. Still doesn't fit. But okay, this is a depth 2 decision tree, so I'm splitting. In fact, I'm making the same split, which makes sense because of this greediness that we talked about last time. It doesn't think ahead and say, oh, I'm going to be depth 2, so what's the optimal tree? It just does the best split at the top. And then for each of those sub-nodes, it splits again. And now I have something that can at least predict 4 different classes. So until you get the depth enough that you're predicting all 10 numbers, this is kind of a silly model. But OK, we can calculate the error rate here, and it's lower. So we could do that. Maybe we want to comment out the visualization and zoom back in, but we could make the depth even more. And the error rate keeps getting lower. And then this brings us to one of our key questions of the day, which is how does the depth of the tree affect this error rate, soon to be called training error? And so here's some code that computes this. It's going to try the depths from 1 to 20. For each of those choices, it's going to create a decision tree object with that depth. It'll fit, it'll predict, it'll do that same thing we've just been doing. This is just a slight convenience that you can take the mean instead of taking the sum and dividing by n. It's exactly the same thing. That's what the mean does. And then we can plot it. And this is what we see. So in fact, it seems like we can get lower and lower error as we make the tree deeper. And we can look at -1 in Python just gives you the last element of a list. Because it kind of looks like we're reaching 0. So we can just print that out and see that we are actually reaching 0. Which makes sense. We talked about it on Monday, in fact, that if you keep splitting and splitting and splitting, you should be able to reach 0 training error. Because if you really wanted to, you could make each example its own leaf, but that's not even necessary, most likely, certainly on this data set. We don't need to do that, probably. Right. OK. So this decision tree gets 100% accuracy on the training set. And the question is, how happy should we be about that result? Have we solved the problem of handwritten digit recognition? And if not, why? Name?
Sorry, Kyle.
Kyle.
This would be back to the previous question. If you were to have two of the exact same pictures, I guess, with different outputs, would it be impossible to get
Yes.
perfect?
Thank you for bringing that up, Kyle. And that goes back to the point of Fed?
Fed, yeah.
Yeah. One way to not be able to reach 0 error is if you had two examples with the identical x and different y, and then you would never be able to get 0 training error. Yeah. Dave.
Just wondering, but for the value array, if we have two numbers that are the same, do we consider them to be the same, regardless of the actual content of the image?
I didn't understand.
Okay, so you said that the numbers in the value array actually represents the number of black pixels.
Uh-huh.
So say if
Sorry, the numbers, I'm scrolling up. These numbers tell me how many of each class do I have in my leaf. So it's not the number of black pixels. This is saying at the top I have 178 zeros, 182 ones, 177 twos. Yeah. There's a question somewhere else. I guess it disappeared. Yeah, your name?
Eli.
Eli, right.
For the graph that was lower down, it seemed to reach 0 at about 12,
Uh-huh.
which wouldn't that mean that there are 2 to the 12th leaves?
Yes.
So isn't that about the same as the data
I
set?
was thinking that too. The question was, we reached 0 at about 12, which means we have about 2 to the 12 leaves, which was about the size of the data set. We saw the data set was around 2,000. So does that mean that we're splitting every point? So yeah, it's possible that we are, or something close to that, or within a factor of 2 of that or something. But that's not necessary to get 100% accuracy. If you have some similar examples with the same class, you could just split them all together and predict that class, and they'd all be correct. Yeah. OK. So we did this. So the thing we care about in supervised learning is not the training accuracy. It's I trained this on 2,000 envelopes, then someone sends mail tomorrow and I want to read the postal code automatically. but I don't have the right answer on hand. That was the entire point of doing this, is to get something that gives me the right answer. That's the whole thing we're trying to do here. So what we want to know is, how does our classifier or our model generalize to unseen data or unseen examples, meaning you don't have them in advance with the right answer. You only get them after you finish training and you're ready to deploy the model. I guess there's a small distinction about whether you get to know the X values of the test set before or after training, but we're not really going to get into that in this course, actually. Okay. So how could we assess this using the resources we have? Eli.
Split it up into training and test data.
Right. So what we can do is say, I was given, thankfully, 2,000 training examples. I'm going to give up some of this wonderful data and hide it from myself and train only on the rest. And then I'm going to take my trained model and do a separate round of evaluation on this so-called test set or validation set. So we're going to split up our data into a training set and a test set, or training set and validation set. The two are used somewhat loosely, even though I would like them to be different. But anyways, okay. So I'll just use this. Of course, I could implement this by just grabbing the top half of an array and a bottom half or something. I'll just use the scikit-learn split because I think it also shuffles. It picks randomly, which is sometimes very important. So, for example, if the data set was sorted by the y value and you split it in half, then your training set would all be the 0s through 4s, and the test set would all be the 5s through 9s. It would be a disaster. So it's good to shuffle, or sometimes even more than shuffle, but carefully split. So I split into train and test, and then I make my deep decision tree. I fit on the train, and now I predict on the train, and this gives me the training error. And then I can also compute the test error by, I'm not fitting again, that's the key thing. I'm fitting on the training data and predicting on the test data. And then I'm comparing to the true y test, which I have because I set it aside on purpose. But normally, when you're testing the thing, you don't actually have the right answer. And I'm getting higher error. So you don't want to deceive yourself into thinking this thing is perfect. It actually makes errors 14% of the time, which is maybe a disaster if you're then sending mail to the wrong province 14% of the time or something like that. So punchline, training error is not the whole story. Training error is not the thing you care about. Test error is the thing you care about. In other words, the ability to generalize to new cases. It is hard to assess test error because we don't know what we're going to have to do later or what the right answer is, but we can approximate that by withholding part of our data set and using it as a proxy for the future task that we're going to do. And I would prefer to call that a validation set, but people also call it a test set. Yeah, name?
Yu-Chen.
Yu-Chen.
What's an optimal test size?
What's an optimal test size? Right, so here I've picked 20%, I think, for test. So there is no single answer for that, but why don't we discuss what goes wrong in the two extremes? So Yu-Chen, if I use 1% of my data for test, why might that be a bad idea?
Not enough training. You don't get the amount of output. You won't be exposed to the amount of inputs and outputs.
Right. So if I use 1% for test, then that tiny amount of test data may not be a good reflection of the stuff I will have to do, because maybe there's just one case, and maybe it's a really easy case or a really hard case, or there's no 3s in that test set, but I'm really bad at 3s, or right. So it's not a good approximation of the thing we care about, test error. But on the other hand, if I use 99% for tests and 1 for training, then what happens?
You might get lucky and just have the ones your predictor is very good at.
Okay, so I might get lucky. That's fair. I would say that if I use 99% for test, then I'm doing a better job of assessing the test error, but the model that I'm testing is not going to be very good because I hardly used any data to train it. So it will not really be, at the end of the day, what often happens is when you're really done, you might retrain on the whole training set at the very end to not waste any data when you're done evaluating and all that kind of stuff. But if you only use a tiny bit for training, you're not, those models trained on 2 data points are not accurate reflections of the type of models we're planning on deploying. They're just these tiny models with very little data. So in either case, we're not getting an accurate reflection of something that we care about. So I know I didn't give you a quantitative answer to your question, but at least it might help you understand the trade-off in why you may want to use more or less. Yeah, your name?
Mariam.
Mariam.
Having a fair set of training set, the fair number of training set and testing set, there is no relationship between test errors and
The question is there a relationship between test error and training error? So we'll come to that now, in fact. Okay, so this next part. So there's a word, very important word, overfitting. Roughly it means I did well on the training but not well on the validation, or I did much worse on the validation set. I would like you to think of overfitting as I adjusted my model to accommodate the peculiarities of the particular training set that I was left with. I got too good at it, and therefore I learned things that weren't actually right, and therefore I did bad on the test set. So we'll get more into this in a minute, but let's first make this plot and then get back to PowerPoint. Okay, so this is the same plot as before, but on the same axes. I'm going to plot the training error and the test error versus the depth of the tree. And what we see here is, at first they both go down because we don't really have to worry about overfitting when we're going from depth 1 to depth 2. We're in such a disastrous situation in depth 1 and depth 2. In fact, we saw that we weren't even allowing ourselves to predict all the integers for that matter. So things are just, whatever you do, adding a little bit more depth, it's probably fine. The test error is slightly higher than the training error, but they pretty much track each other. But at some point, we reach this point where we're overfitting. So in a way, that gap you could think of as the overfitting. And we're getting really good at dealing with the training set, but that extra getting good at something isn't actually a reflection of the larger task that we're trying to perform. So very much of this course, like I won't give a percentage, but a very significant portion of this course throughout the entire semester is dealing with that gap. How can we get the best of both worlds? Can we come up with methods that push the test error down? Because here, learning what we've learned in a week of the course, we're kind of stuck with this trade-off, and we can't really make test error any better, but it should be possible for this simple data set to come up with something that actually gets really good test error. Okay, I'm way behind, but that's fine. Let's see how many slides we can get through. Yeah, what's your name?
Matthew?
Matthew.
Can we expect the test error to remain somewhat constant, or would we expect it to go up?
Can we expect the test error to remain somewhat constant? So sometimes it plateaus and sometimes it actually gets worse. Okay. So we just introduced this concept of training data and testing data. We're going to use the notation with a tilde on top, a squiggly thing. So when you see X or Y like that, it refers to the test case. Everything else is the same. But we do not have those Y test cases. They are the other things that we're looking for. Okay. I think we talked about this. It's just notation here. Predictions are hat, test data is the squiggly, and we want to do a good job of predicting those things. Okay, I think we talked about this. All right, so here's a nice analogy for something that you might relate to in terms of overfitting. Let's say I give you a practice midterm, and you use that to assess how well you're doing in your studying. But the thing you care about is actually your ability to perform on the actual exam, but you cannot see the actual exam when you're studying. So the studying is like the training or the fit call in scikit-learn. And you don't know yet what that's going to be. And it may be the case that you can do extremely well on the practice midterm by just memorizing everything on it, and then your training error, meaning you can go back and repeat the practice midterm and get 100% because you just wrote down all the answers and put them on your arm or whatever people do these days. But it's not going to help you on the actual midterm. And again, with the decision tree, right? I mean, it could have just stored the entire thing and got 0 training error. But that's not going to be useful. So that's this distinction between memorizing and learning. And we call it learning. We're actually, I don't know if understanding, but learning if we can get something out of it that actually allows us to generalize. Any thoughts? Okay. So what we'll call in this course the golden rule of machine learning is that the test data should not influence the training data. So the real test, that might be impossible if you don't have the test data, but say if you've split into 2 data sets like we did in the code, but then you're somehow cheating and allowing the test data to influence your training, you've compromised the integrity of that test set. Because the whole point of it was it's a new case that you haven't seen before. Yeah. I mean, I would say that the analogy is that maybe, I don't know, maybe you're studying with someone, they're sitting next to you, and they have the real midterm that you're going to have, and they don't show it to you, but you're kind of sitting next to them and seeing what they're putting on their notes, and you kind of get a sense of what's going to be on the exam. Then, yes, you'll do better on the exam, but that's not the goal here. The goal is to actually learn, and so in a real situation that you would definitely not have access to, you won't be doing a good job. So this sounds like, why would I ever do this? But it actually happens sometimes, and it's something we need to look out for. You might be using the test set in ways you don't quite realize, I guess, and we'll get to that. Okay. So is learning possible? So not always. I mean, the whole premise of this is that your training data and your test data are related in some way. If your test data was just random numbers, there's no way you could learn to do well at that, because whatever you learned, it's just random numbers. So how could you predict random numbers? Well, you can't, right? So we operate in a world where even if we're not explicit about it, we're assuming test and train are related in some way. And in terms of learning theory, which we don't really get into in this course, this assumption is the IID assumption. So if you've taken a probability course, this idea of being independent and identically distributed, we're basically assuming there exists some probability distribution. We don't know what it is, but the test data and the training data are both being drawn from that same distribution, and they're not going to be the same, but they come from the same place. So in terms of being identically distributed, we expect that even within our training set, all the rows come from the same distribution, that they don't depend on each other, that's being independent, that the order doesn't matter. And these assumptions kind of seem natural to us. I mean, if we shuffled the order of things, that shouldn't matter. And so in terms of a deck of cards analogy, if you picked a card, put it back, shuffled, picked another card, those would be IID. But if you don't reshuffle or you don't put the card back, then they wouldn't be. So the thing is, most of the time we can't prove that this is true. We just hope it's true. And that's really the point to be made here, is that you should be aware that underlying everything you're doing, there is some assumption. And one of many failure modes of all this machine learning is that this assumption is grossly violated and your test data is completely different. So maybe all the digits in your training set were written by me, and then you wanted to use it for digits written by you, but I write my 4s like this, and you write your 4s like that, and it doesn't do a good job predicting 4. So that's an example of this assumption being violated that could actually happen in a real situation, and you need to be aware that this could be a problem. And I'm not stopping for questions as much because I'm pretty behind. So in terms of the food allergy thing, there's many ways in which this assumption is violated. Certainly, the days are not independent of each other. Besides, you might eat something today and get sick 2 days later, or it might be a combination of things. You might change over time what you eat. So I guess what I really want to say about this is it's usually not going to be true, but you need to kind of think of how bad the situation really is, because even your validate, we talked about how training accuracy is really not the thing you care about, but even validation accuracy, meaning you split up your data, that could still be quite wrong. And you don't want to deploy a system when you're working for a company or something and say, oh, I did really good validation error. I took Mike's class. He said validation error is the most important thing. And then you deploy it and all the customers are miserable because your whole training set to begin with was just very different in nature from what you'll actually be doing. And there's many examples, like with images, it could be different lighting conditions, or it's not hard to think of how that would happen in many different domains. Okay, kind of said this. We'll use the notation E for error, so training error and test error. Yeah. We'll call approximation error the difference between training error and test error. So that was that gap. We had the two lines, and the gap between them was what we'll call the approximation error. And at the beginning, the approximation error was small because train and test were tracking each other with the decision trees. But the training error was pretty bad. We just didn't have anything good. And then later, we had something good. We had training error of 0, but this approximation term was bigger. And in general, the approximation term tends to get bigger as the model gets more complicated. Because if the model's arbitrarily complicated, like a super deep decision tree, you might always be able to get 0 training error, but not necessarily test until you get this gap. And the more complicated it is, the more it is free to do silly things to accommodate the peculiarities of the training set. Okay, so this is an important slide. The fundamental trade-off, as we're going to call it in this course of machine learning. We will talk about this again and again and again and again in this course. How small can I make the training error? We did a great job of that with the deep decision tree. Versus how small can I make the approximation error? In other words, train and test error being similar to each other. And again, it has to do with this thing of simple models versus complex models. And you will see more examples throughout the course of what we mean by simple versus complex. And there are these words, overfitting and underfitting. And overfitting means that this approximation term is very big. So you're doing a bad job of approximating test error by training error. And underfitting is the other case where, just like the decision stump, you weren't even doing a good job on the training set. So a lot of terms today. Any questions or comments? Name?
Xinyu.
Xinyu.
So is the test error just like assumed to be a constant then?
Is the test error assumed to be a constant? What do you mean by constant?
Because here you're just subtracting training and adding training back on to all.
This subtracting and adding, I'm going to go back one slide. The point of this is to say that we can think about test error as coming from two sources. One, I'm just not good enough at the thing, like I have a decision stump. And another is I thought I was really good at it. I was really good in the training set, but I went overboard, and so I'm actually doing badly. So we just write it like this to think about test error in a certain way, which is there are these two ways it could arise when we see a bad test error, and so that we can think about it. Name?
Shayan.
Shayan.
So over here, overfitting was basically caused by changing the hyperparameter to increasing it. Can it be caused by other factors like having too much data or having?
The question was, overfitting here was caused by changing a hyperparameter. So in this case, the maximum depth of the tree. Can it be caused by other things like having too many features? Yes. We could also think of that as a hyperparameter in a way, but we will get to that later in the course. I know I didn't repeat everything you said. You also said or too much data. So no, having more data is exactly the thing that prevents overfitting. Because if you had infinite amounts of training data, you would know everything there is to know, in a sense, about this distribution that we're looking for. And so if you had infinite amount of training data, there would be no overfitting because there would be no peculiarities of your particular training set that could throw you off. But you also said or features, and there I'm going to say yes, because if you had a bunch of bad features, that could cause overfitting, because again, they're kind of like red herrings that you might fit to that don't actually have predictive power. Okay, 4 minutes. Said that. Already showed you this. Sometimes it goes up, sometimes it stays flat. We talked about that. Validation error, we kind of talked about this. So again, loose usage of the words validation versus the word test. My preferred usage would be test is that hypothetical thing that you eventually have to do, and validation is the portion of your training set that you withheld in order to approximate test error. However, the terms tend to be used pretty loosely, such that even the scikit-learn function is called train test split. I wish it was called train validation split, but we have to live in the world the way things are. So test sometimes actually means the portion of your training data that you withheld to do validation. Okay, so in other words, we already talked about this. We just didn't have the word validation appearing on the slide until now. Fine. Split in half. So yeah, you should be thinking of this as the split being a horizontal line, right? Because the rows are your objects. We're splitting horizontally. These are training, these are testing. You should not be thinking of it as splitting this way, where I take half of my features for this, half of my features for that. That wouldn't make sense. So we're splitting the objects, the data set. We did all this in code. We did the train, which is called fit in scikit-learn. We did the predict. We got the y hat. We did precisely this. We talked about how it should be random. Great. Okay. Skip this. Hyperparameters, right. So we talked about parameters versus hyperparameters. In this case, the only hyperparameter we've seen is the depth of the decision tree. We will get more concrete about this in the next few classes. And you'll see more examples of what's a parameter and what's a hyperparameter. Good. But yes, roughly hyperparameters are things that control the complexity of the model, and we tend to pick them using our validation set. This is not so critical right now because we're just going to see this so many more times. It'll be more concrete. Sorry, I don't have time.
Okay.
We can talk after class. Okay. Right. So what this is saying is I could go back to my plot from the Jupyter notebook where I showed the training and validation error in the blue and orange curves, and I could say which depth gives me the lowest validation error, and I could use that to pick the depth that I actually thought was the best depth. So training error will just tell you pick depth 1,000,000 because it's the greatest thing ever. But if you looked at the validation error, it might tell you depth 7 is the best or something like that. And you'll certainly be doing this on your assignment 1. Okay. Pretty low on time here. So there seems to be some actual non-trivial content left in the lecture, so I can't just squeeze it all into 10 seconds. So I will finish this up next class before we properly start the next lecture.